nice and cozy. The front row seats are, a lot of them are empty.
I can send you the paper.
Thank you all for joining. My name is Fareed Rashad. I flew all the way from Holland just to organize this meetup. I call myself an excited community member. I like to call myself part of the inner circle of Avalanche. And so we're here at Distributed Global. Want to thank them for having us be in this space. Kevin Sekniki is here, co-founder of Avalanche. He'll do the rest of the talking. Please give him a warm round of applause for sharing this evening with us.
Thank you. Okay, so first of all, thank you guys for coming. It's 7 p.m. I realize I may have made somewhat of a very technical talk, and given the time of the day, I might have not been such a great idea, but please bear with me. I hope we can go through some exciting stuff today. As a show of hands, how many of you guys are really into cars and like really understanding engines and like motorheads basically? No, okay, so I'm really into them. I love them. I kind of like study them a lot. I go through like click holes on YouTube. And really what I want to do is sort of kind of guide you guys through the process of how you would effectively build a car. You have the engine, how you would design the system around that engine, all the things that you need to account for from beginning to end in order to get something to really be something like great, something amazing, a system that we've never seen before. Of course, the car in this case would be a new blockchain platform. But we'll start off by talking about the engine, what really drives blockchains, and then work around it with those primitives that we introduce to build a possibly really interesting new type of blockchain system that has interesting new properties that we haven't quite seen before yet. This is not working. Oh, there we go. Oh. I think I've done this before. There we go. Okay. So, a very small primer of consensus. It gets super messy. There's all kinds of network models you have to take into account, whether the system is Byzantine or crash fault tolerant, whether we are probabilistic or deterministic, whether how our shared memory or message passing. But you don't have to worry about any of this thing. We're only going to focus on the two sort of major classes of types, rather, I would say, of consensus protocols. We start with consensus, and we really only go into two types: voting-based consensus protocols and something called longest chain consensus protocols. Go back. Okay, I'm gonna not do this anymore. It's not working. Second. This.
Do you want me to move there and hit it for you?
No, I think I'll just move this over. Okay. So consensus until now has basically been through two families: Nakamoto consensus and voting-based consensus protocols. Nakamoto consensus is what Bitcoin introduced, of course, and classical consensus protocols have actually existed for many, many years in distributed systems literature since actually the 70s and 80s with the work of Leslie Lamport. So Nakamoto, you know very well. The basic idea of Nakamoto is you have a system of a chain of blocks, and every new block is introduced by creating some sort of proof of work, rather solving a particular nonce that has a particular weight of difficulty, and that's what gives you a ticket or the right to create a new block. Anything less than that difficulty doesn't give you the right, and therefore you cannot become sort of a temporary leader and introduce a new block in the system. This is a basic primitive of what longest chain works as. Actually, do you want to maybe go
Yes.
into that? That'd be fantastic.
I do.
I've tried that before. It never works. So the nice thing about longest chain protocols is that they're super scalable. You can have thousands of nodes. Unfortunately, they're also super limited in the way they're constructed. You literally have fundamental limitations in the number of minutes that you need to wait in order to allow enough propagation of the blocks across most of the hash power in the network. In fact, if you violate that assumption, basically you make the block times too short, you end up effectively partitioning the network. You have a set of network nodes that are super fast and they create blocks faster than everybody else, and everybody else is effectively partitioned and able to catch up. So this limitation is what places an upper bound, sort of like a maximum number of messages that can fit within a sort of limited amount of time. And it does not matter how fast the fastest nodes in the network are, you still can you must have to wait as long as it takes for every block in the system to propagate. So this makes long-distance systems, in fact, that it's a fundamental limitation of synchronous protocols, which is what long-distance chain is. This is what actually makes them not fast. They can't go at very high speeds. Next slide. Consensus, the classical consensus protocols, on the other hand, they're actually super fast. The reason is because all they need to do is just collect a bunch of signatures and then move on. So you don't have to wait this limited time in order for blocks to propagate. You just get the required number of signatures for a quorum, and then you know for sure that a decision has been made, and I can move on to the next decision. Unfortunately, in the decades of classical consensus protocols that we have had since, there was this famous Paxos paper by Lamport in the 90s, but the consensus protocols in classical domain has existed since the 80s and 70s. Since then, it's only basically been the same core construction. We sample everybody else in the network, we get their state, and then we make progress to the next state. It's effectively, I'm a leader, I tell you guys, here's what the value is. You all talk to each other, all to all, and then you make progress in the next phase. So this all to all requirement, while it can be fast in very small settings, maybe in a room like this, it obviously cannot scale to a very large number of participants. So while you get high TPS, you do not continue this trend once you get to several hundred nodes or even thousands of nodes. So there's been obviously a lot of work on trying to improve these pitfalls. And we're trying to design sort of a really interesting new engine. This is what we're trying to do, right? We're trying to build a really cool car, and we have to start with the engine. And if we start with somewhat of an engine that has a lot of limitations, and you try to augment it with bells and whistles, you end up with a lot of really great work in distributed systems, both on the Nakamoto families and then on the classical style, but that fundamentally introduces more complexities. A really good example is, for example, the notion of introducing subcommittees to classical consensus protocols. So instead of using all-to-all, we all elect a small committee, and we use that committee to give us the next set of blocks. This introduces a crazy amount of complexity, VDFs, VRFs, all kinds of stuff that we need to use cryptographic primitives in order to securely elect this committee in a way that doesn't violate, for example, the number of adversaries that exist within the committee. Nakamoto's obviously introduced a whole lot of other different scalability solutions. Layer 2 is another one, although Layer 2, of course, still has the same latency requirements as the Layer 1, which is what the number of the underlying system requires. There's been sharding that has been proposed for both systems, but also sharding is as fast as the slowest shard allows, and the more communication is required between each shard, the higher the contention of the system and the slower the system is. So it cannot really scale to very large numbers. So we're trying to design a new engine. Is there a different way? And potentially, yes. So the interesting thing that Satoshi introduced is this notion that we don't require a guarantee probability 1 of consensus in the safety aspect. That's too strong of a requirement. The way Nakamoto works is that you have a bunch of blocks, you see some depth in the blockchain, and then you, in turn, locally, get to decide when the decision has been made based on your security requirement. The longer this block depth is, the higher the guarantee that you're safe, that you can never be spent on. So you really receive your funds. And in fact, the original Bitcoin white paper says 6 blocks, although that's actually too high of a safety failure probability. But if you go several dozens or hundreds of blocks, that probability starts going to 1, but it never quite reaches 1. And this is in stark contrast to what all-to-all voting in classical protocols provides you. All-to-all voting in classical protocols provides you with exactly probability 1 guarantee of being safe, as long as the threshold number of signatures is met. As long as I get 2/3, for example, let's say quorum within this room, everybody 2/3 says yes, we are done. There can never be a safety violation, as long as we assume that 1/3 at most of us is actually adversarial. So what we could do, an interesting idea, is to basically merge that idea of never really quite reaching probability 1 of safety into voting-based protocols. And that's exactly what we're going to do. So in classical voting protocols, the way it works is that you have a bunch of replicas, which are the nodes all the way on the right, and then they propose a particular value, whatever the value may be. And that value, I represent that value in the state. So the way you make progress then is after taking the values from everybody, you apply them to a particular function, and now you move on to your next state. We say, Alice pays Bob. Everybody says Alice pays Bob. That is your proposal. As long as 2/3 of them agree that Alice pays Bob and Alice pays nobody else, then this every node will accept that proposal. We'll say, okay, we're going to finalize that Alice pays Bob. So instead of having this super strict requirement, we're only going to sample a small set of them. So basically, we select a very small subset, and we ask them, okay, what do you think? Who do you think rather that Alice pays? Does Alice pay Bob, or does Alice pay Charlie, or anybody else? And turns out, this is a pretty powerful little construction. Yeah, that's good.
Good,
Go ahead.
okay.
So the Snow family, it's basically a different protocol family. It provides a probabilistic guarantee onto classical voting-based systems. It's a state. It uses subsets to provide strong statistical guarantees of what the system state is, instead of sampling everybody in the network. So basic mode of operation is super simple. I'm going to explain to you guys the core primitive, which happens to be binary consensus. So a little bit of a detour. When you talk about distributed systems consensus, you usually build distributed consensus via the notion of binary consensus, which means that as long as we have a mechanism, an algorithm, to decide between two values, then we have an algorithm to decide between any arbitrary number of values. And we can use that decision mechanism of two values to basically build a blockchain, which happens to be many values consecutively. So in order for us to build this new system that we want, let's start off with the binary consensus case. In this case, I'm representing a bunch of nodes sitting in a circle, and they're all labeled either red or blue. Red, for example, could be Alice paying Bob, and blue can be Alice pays Charlie. Now, Alice only has a limited amount of funds, and only one of these two transactions can go through. So our end goal is to have every single node in the system end up the same color, or rather accept the same proposal. So the basic mechanism is that every node, independently of each other, will sample and query the other nodes in the network, asking them, what is your preferred proposal? Is it Alice pays Bob or Alice pays Charlie? Every node does this independently of other nodes. They do not wait for other nodes to move into rounds. They do not have a notion of rounds. They just do it entirely independently. In this example, red samples a blue, a red, and a blue. We've set the system to be such that a simple majority wins out. So this node will now become a blue because it's sampled blue majority. Excellent. Which is the case here. And this process is repeated. Yes?
Can the different nodes, can they decide, like, pick their own sample size? Or is it like a...
They can. We provide a default, but they can choose their own sample size, yes. And the higher the sample size, the higher the security guarantee. But there is interesting trade-offs between latencies and the size.
So it's like ultimately each node, they kind of decide on whether they want to be red or blue, but they can use their sample information to kind of help them, advise them what other people think.
Exactly. So every node can start off at any arbitrary proposal, any arbitrary color. And by doing this repeated sampling, they will converge to the same proposal. Okay. That's the whole point. We want to all get to the same decision. I'll make a comparison to how this would look on an actual blockchain in a second, a few slides. But okay, next slide. Next. Okay, so I've been told this is a confusing slide, and but let me kind of guide you guys a little bit through this. Effectively, what this is saying is that once you have the system in a particular region, which happens to be, in this case, let's suppose we have 1,000 nodes, and somewhere between like almost 850 of them to 1,000 of them are the same color, let's say red, it becomes effectively impossible for the system to move to the other direction, which means most of the nodes become blue. So once you move towards here, you're in what we call an irreversible zone. The system stays in all red, it does not move back. And it's really hard, even with Byzantine adversaries saying, no, Alice space Bob, not Charlie. Even if the Byzantine adversaries say that constantly, it doesn't matter. The correct nodes will not change their minds. And this is what provides the security into the system. Okay. Cool. So we got some base primitive. That's interesting. Some of the key properties that it provides is that the number of nodes is effectively independent of, the number of nodes to sample is effectively independent of the actual network size, which is a really cool property to have. It doesn't matter whether you have 100 nodes or 1,000 nodes or 1,000,000 nodes, you simply always sample some constant size of them, let's say 20. And you will see the performance, I'll show some graphs, of the system exactly displays this. It doesn't matter the number of nodes, the throughput will basically stay the same. So it's a really a nice property to have. We don't have trusted setups, no VDFs, no VRFs, nothing like that. And it's super simple. And another property that's really interesting is that unlike other, unlike classical voting-based protocols, it provides sort of a built-in mechanism to make progress towards one decision. Classical protocols, they require a leader, because otherwise they will be stuck. A leader comes in and has to say, guys, Alice pays Bob, or Alice pays Bob. If nobody dictates this proposal, classical protocols cannot make progress. Whereas this primitive will in fact make progress without a leader. Okay, so we're gonna map this directly into our usual world, which is the world of blockchains. And basically a sequence of linear blocks. And we'll build really two protocols. We'll build a protocol which we call Snowman, which is just your standard good old blockchain, a linear sequence of blocks. And we'll also build Avalanche, which is the original white paper that was based on these core primitives, which builds that. Okay, so the leaderless version of Snowman. It's actually much simpler than it looks here. So looks a little bit intimidating, but I'll go through it one time. So what you're seeing here is the operation of the system into, this is not phases, this is more of like, in time, how the system looks. Let's start off with the top here. We have a sequence of blocks, bi-1, bi, and then at some point, at block height bi+1, we have a fork. This happens constantly in Ethereum. For example, the fork could happen because a transaction here says Alice pays Bob, and the transaction over here says Alice pays Charlie. Only one of these two blocks can go through, not both of them. Otherwise, it would be a double spend. So the way this would work in Snowman is that every node, as I mentioned, samples for this height a subset of other nodes and requests them. Which is your favorite block in this height? Some nodes will respond with, this one is my favorite one, and some other nodes will respond with, this one's my favorite one. Quite literally, like suppose everybody in this room, we split about 40% says that I would prefer the top fork, and the 60% says I prefer the bottom fork. Why is this split happens? By simple randomness, for example, in network. It just so happens that somebody proposes a block with Alice space Charlie, and somebody else proposes another block with Alice space Bob, and Alice is malicious, it's trying to double spend. Okay, so in the next phase, everybody queried some other subset of nodes for their preference. And they got some answers. Some people said, okay, I prefer the top one. Some people said I prefer the bottom one. But turns out, as I mentioned, the repeated sampling drives the network towards convergence of one color. This is what I mentioned, the inherent method by which we converge. We don't need a leader. So just the fact that we're randomly sampling people, we're going to bias the network more and more towards whatever the majority color is. So if initially was 40% red, it now is going to be significantly less biased towards red. It's going to be much more blue. And this process continues. So now new blocks are being introduced, and this fork over here is losing preference. All these new blocks are gaining preference amongst other nodes in the network. At some point, very few people will prefer this fork, and now we can basically get rid of it and create a whole new chain with that everybody prefers. Does it? Yes.
Can a node see in real time how the rest of the poll is going?
The rest of the poll, which poll?
As time goes on, can a node see the polling take place?
So a node
queries
other nodes, and then all it gets back from them is the preference of that node at this height. So you tell me, if I query you, you tell me, do you either prefer this one or this one? That's all you tell me. And based on whatever majority I get from that, I switch my preference now. Let's suppose that like I queried 10 of you guys, and 8 of you said, this one is my preferred one, now this one becomes my preferred one as well. It's like we pick up the phone and we say, who are you voting for?
But it's publicly published after the first round.
I don't publish, yeah, so after I change my preference, other people will query me and they will say, what is your preference? And I'll say, yeah, this one is my preference because I queried before and that one was the majority and now I'm on this board. Does that make sense? Cool. Yes?
So in the beginning, if we assume that there is at least 80%, 20% split on color,
Yes.
then it's pretty safe to say that it would probably convert to whatever is
80%, right?
Yes.
But how do you know what the distribution is at the beginning? Like, what if it's very close to 50-50? Like, isn't it?
Perfectly fine, yes, great question. So you don't actually know what the initial distribution is. What this protocol provides you is the ability to converge towards one side, and then what you need to do is detect that you have gotten to that, remember that zone where you're like supermajority, the irreversible zone? You need a way to detect that you have reached that zone. And the way you detect to reach that zone is what we go through consecutive successes of majority queries. So basically, if I see 10 times in a row that everybody votes majority, vast majority towards one side, I can tell myself, look, it's very, very likely that that one is the actual preferred majority. So it's just simply a statistical measurement of the number. And it happens to be consecutive, that's what it shows up.
Okay, so the mechanism is for picking one of the two options. It's not necessarily determining which one is correct.
Yes, exactly right.
Okay.
Exactly right. I'm assuming that every transaction here
Picking one of the two.
Exactly. Any one of the two. It doesn't matter which one of the two. Of course, if something is invalid, most will say, I'm not going to accept this because it's invalid. Absolutely.
I'm sorry. Apologies.
Oh, no, please.
When you're in that, right, and it goes back to exactly what you said, right? So you're converging one
Yes.
side or the other.
Yeah.
But you can have a group of actors.
Yes,
If you will.
right.
And I'm sure you'll probably get to that, so I'll be
Yeah.
patient. So I was just trying to lead into that and saying, okay, they can branch off and drive a certain point.
Exactly right. Yes,
What
absolutely.
are the issues to kind of handle that?
Absolutely. Yeah. So, great observation. So in the leaderless version of Snowman, there happens to be in the very theoretical model where a adversary has full knowledge of every state in the system, can see what everybody is at all times, and can send queries at the really appropriate times. There happens to be a well-known theoretical result that says that square root, we can make progress in logarithm number of rounds to confirmation if the number of Byzantine adversaries is less than square root n. And this is if the system is exactly split in half. If the system is split, let's say 60-40 and so on, then it's harder for Byzantine adversary. Simple heuristics to sort of perturb the network will make it's very unlikely the system will start off at 50-50 split. So you can go, usually there's actually really quite a bit of heuristics that assuming some synchronicity, you can get the system to be only univalent to start off with. But you can also augment this with the leader. The leader effectively just becomes a contention reduction mechanism. All it does is it tells us we either let's start off with all red or all blue. So super straightforward implementation. Any more questions? I think you're not satisfied with me, but we can take this
Okay,
offline.
we can take it later. It's all
Absolutely,
good.
absolutely. Okay.
Thank you.
Okay, so the Avalanche implementation is effectively just a sort of parallelized version of Snowman. Instead of having a linear sequence, what I'm going to do is I'm going to take blocks in this DAG, which represent transactions, and I'm just going to arbitrarily create other blocks that attach at various different parts of this DAG with the following property, such that if I sample successfully for this transaction, it implies transitively that everything else up all the way to Genesis is also preferred, is my preferred branch. So what this provides you is that it entangles a lot of decisions from each other. So if Bob pays George and Charlie pays Fiona here, these are two independent decisions. They can happen simultaneously. Different nodes can work at different parts of the DAG. I don't actually need to linearly order all these transactions. What this provides you is just higher scalability, or rather high performance, because you just work things in parallel. Okay. And the other thing to note is that it doesn't actually matter what the Byzantine adversary creates here. If the Byzantine adversary creates a massive sub-DAG, the structure of the DAG does not confer any additional power to the adversary. We will still have to query everything. So there has been some proposals on DAGs. I think the Ghost protocol has a notion where the structure of the DAG actually implies something about decisions in the system. Here, not the case. You still have to just sample everything. So that attack does not exist. Okay, cool. So the most important thing, these numbers, you can optimize them quite a bit. I made a thread on Twitter at some point on how to fake your TPS numbers by making all kinds of hokey stuff. We didn't do any of that. This is an actual real implementation, full implementation of Avalanche with simulated latencies, geo-distributed on AWS, running at 125 nodes all the way to 2,000 nodes. You can see that basically the instance in C++, the performance stays effectively the same. It doesn't really matter what the number of nodes is. And then the final thing is latencies. So an interesting thing that I noticed that was confusing, and this, you can go to the next slide. This was actually just a discussion from last night. There was some confusion on how it's possible to get to sub-3 second latencies for confirmations if you're doing multiple rounds and each round requires full round trip. The reason is simple: pipelining. I don't actually need to wait for a full round trip per round in order for me to make progress. I just take a bunch of transactions that are sequential for example, in the chain, and just query them one by one, immediately, one after another, and I just wait for the responses to come back. So I don't actually need to wait for every single one of these rounds to confirm. So pipelining is what provides you the ability to confirm so quickly. Okay. Okay, cool. So that was maybe quite a lot. Hopefully you guys understood it though. So we want to now sort of focus on the architecture, kind of what we're building here. A lot of blockchains are monolithic, and we've seen this with Ethereum, Ripple, and so on. Not blockchain, Bitcoin. They have a single ledger, single validator set, single virtual machine. So it's a nice architecture to start off with, but we want to build something really neat. And what we want to build is effectively a system of multiple different types of ledgers. And we'll get to that in a second, so let's move on. The design, give you a second here. The design basically of what current blockchains look like is, the analogy that I like to use is if we build the internet in a way where every single request goes to one global router. This is obviously the wrong way to build decentralized applications as well. Obviously, of course, the internet, this is not how the internet is built. And so we're going to apply the same architectural design of how the internet is built down to decentralized networks. So, again, as I said, one coin, one streaming languages. Existing systems are also extra legal. So if I want to deploy for example, a smart contract on Ethereum, it's a really powerful system. Unfortunately, it does not provide sort of extra protections. It only provides whatever protections the base sort of lowest common denominator nodes provide to me. I don't have any recourse if I deploy a really important application on Ethereum and it just ends up, not surviving over the long term. Like it could be, for example, house titles and so on. These are really important applications. I want to have a lot of guarantees. In fact, potentially even legal guarantees that my system is going to be safe. So what you do is you effectively build a disintermediated sort of system, a system of a network of multiple types of distributed ledgers communicating together. They have different types of validator sets, which you can either define or allow people in the open to join in permissionlessly, as well as they implement their own functionalities. They can implement their own virtual machine. They can import their own feature set, like maybe privacy, plugins, and so on. So, next slide. I want to give you basically sort of top-down description of how it would look like if you wanted to launch your own subnetwork within Ava, or rather your own application. you start off, oh, this is quite hard to see. Can you guys see this? Can everybody see this? No.
Just read it.
Just read it.
Okay, sounds good. So you start off by asking, do you want to use an existing network? I'm going to only give you an example for the use case where you want to, for example, launch a new token that represents bike insurance. So you can either launch it on a new network, or you can use anything that's existing. For example, there's going to be Ava ETH, which is effectively a wholesale import of the Ethereum virtual machine with its own value settlement and everything. You can just use that exactly as is, or you can launch a new one. So suppose we launched a new one. The next thing you can customize is, can I build, do you want a DAG, or do you want a linear chain here? If you want a DAG, because you maybe don't care about linearizability, go ahead and use it. You'll get higher performance. If you absolutely require ordering, you'll go ahead and use a DAG. The next question is, do you want to use an existing virtual machine? You can use any existing virtual machine that we've imported with this notion of what we call a plugin, which is basically extensions, functionality extensions, like the EVM, WAS, and BTC script. Or if a virtual machine that you really want doesn't exist, you can just build your own and directly import it into the subnetwork. And then finally, let's suppose that I choose WASM, and then do you want to import any additional functionality? So for example, do you want ZK keys or any other thing that you may want for your chain? You may want ZK keys. Do you have a question?
Just an example, let's say when I have a ERC 721, which
Yes.
somehow utilizes Bitcoin,
Yes.
can I, so basically.
Your CTM utilizes Bitcoin script. I'm not sure how does Bitcoin script understand? It doesn't understand.
No, so I'm trying to understand it. We're like totally different virtual machines, and we can merge like different.
Yeah. Some virtual machines cannot coexist.
Okay.
Yes.
Okay.
We're actually we're thinking of internally. We had this design discussion at some point. We're thinking of the notion of even allowing such things to do
Okay.
internally. We didn't come up with very compelling reasons why you would want to use that, and we just decided, maybe it's not a great idea. But if you have a compelling reason, absolutely, we will take into consideration. We'll love to hear your thoughts. So yeah, if you import the Bitcoin script, it's just Bitcoin script in that particular segment. And then finally, you want to just define your validator set. So you can either use an existing system, like an existing set of validators which already exists in Ava. Actually, every validator you can possibly use is by default an Ava validator. This is like what provides the baseline security guarantees, and it's what also provides certain invariants that are required when doing atomic swaps for security guarantees in the system. So you can define specifically yourself. I want you, and you to become part of my network, and we'll enter externally into a legal contract, or I can also make it permissionless. So anybody can come into my subnetwork, stake, and become a validator, and accumulate benefits that you would from becoming a validator of that system. Okay, great. So let's roll. So architecturally speaking, we have the network layer, subnetworks built on top. Everything in Ava is effectively a subnetwork. Even Ava, the Ava token itself, which provides all of the atomic swap functionality in the system, even that one is just a subnetwork. Although it's a special type of subnetwork with index 0. Everything else is also subnetwork. There's many subnetworks that coexist. Of course, on top of each of these subnetworks, it effectively looks like any existing chain that you currently see out there in the wild, like Ethereum or Bitcoin or whatever it may be. So you have the app layers on top. Additionally, you can also choose from the plugin store. So you can add EVM support, WAS support, whatever you may want from whenever you deploy your new subnetwork. And then you can also use technologies like bridges and L2s that are imported sort of as plugins. So I can import a bridge plugin that bridges to Ethereum, like the actual Ethereum network, from my own subnetwork within Ava. So everything is a plugin, incredibly modular architecture. You can just sort of mix and match everything as long as they kind of make sense. And some certain things are something that cannot coexist, but you can sort of get creative there. Oh, and finally, everything per protocol, you can actually define special covenants to where assets can flow. I can say that assets deployed on my network cannot trade with any other subnetwork. So this is sort of the final missing piece beyond the notion of defining my own validator sets. This is the final missing piece that sort of bridges that last bit of functionality required for issuing assets in a legally compliant manner. This is what allows me to say these assets are being replicated amongst certain machines that I have a legal agreement with, and they cannot be traded with anybody else unless they, for example, have KYC, AML done. So we can create all kinds of assets that have legal compliance, but also, of course, anything that may not have legal compliance, although we don't recommend. Okay. All right, so let's wrap up some economics. That's quite a bit, so I'll kind of be short a little bit. Base layer, where Ava sits, it burns fees. We don't actually accumulate fees, so it's deflationary in that sense. But it's inflationary because we mint new coins and they're distributed to the current validator set, which actually happens to be basically running on its own chain. So there is this notion of a canonical staker chain. It's a big metadata chain which sits as a subnetwork of Ava as well. Everything is a subnetwork, as a plugin. And that holds all the metadata information about which subnetworks currently exist, about who the validator set of these subnetworks are, and all kinds of other information you need in order to transact. And all of these, and all economic swaps and so on are paid in Ava, also fees accumulated to the Ava stakers. Finally, I'll keep it very brief on governance. So we don't have, the very powerful governance story that Tezos has, which is everything is subject to governance. We think that's maybe a little bit dangerous. Instead, what we do have is a certain set of parameters that usually are the contentious ones when it comes to governance. And these are things like minting rates. This is a theme that happens constantly in Bitcoin circles. How big should the minting rate be? How many coins should we mint? So these are actually governable parameters for the system, but only to limited ranges. So you cannot sporadically change the minting rate 400% overnight. Okay, and that's basically it. So a few kind of information. Very importantly, we have effectively full support for any smart contracts that you've already built on the EVM. Support them wholesale, run them with thousands of validators immediately as is. If you have anything that you want to run WASM, we will have WASM support as well super soon. And yeah, so this is all before we even launch mainnet. So we'll be launching effectively these linear chains as subnetworks before the Ava mainnet node exists. And on Ava mainnet launch, everything will sort of be put together. We'll have atomic swaps ready. We'll have bridges implemented in place by then, and that's hopefully very soon. Cool. So I think that's it.
Question time. Loud.
Yes.
Questions.
Hey, yeah, thanks for the presentation. It's very, a lot of this to grasp.